Good morning. How many of you are here at an AWS Summit for the first time? Raise your hand, please. Awesome. Welcome. Must be an exciting day. Lots of sessions, lots of fun. First of all, thank you so much for joining us here today. My name is Rajiv Penmetcha. I'm a senior solutions architect in AI and ML at AWS. Today, I'll be covering how to solve common business problems using AI and machine learning. The real star of today's session is Jason Davis from University of Arkansas. He'll be presenting how he solved his business problem using these technologies. So our agenda for today is, I will start with an overview of machine learning, followed by a list of key ingredients that make a good machine learning use case. We'll then discuss some common use cases in machine learning. And after that, Jason will present how he was able to detect weed in soybean crops using Amazon Rekognition custom labels. Now, you may have heard these technologies described in a number of ways. So let's take a step back and level set on what they are. AI is a way to describe a system that replicates tasks which would normally require human intelligence. Many times this involves some kind of complex business decision or complex logic. And all AI applications expect a probabilistic outcome, like a prediction or a decision that requires high degree of certainty. Almost all AI systems are built using machine learning, which uses lots of data in order to create and validate decision logic known as the model. An AI application then feeds input into this model, and the model outputs a human-like decision. So machine learning is the underlying technology that is powering these intelligent systems. Deep learning is a type of machine learning that uses a technique known as deep neural networks. These systems try to replicate how human brain functions. Because of that, they're able to solve much more complex problems than it was previously possible. AI moved from being an aspirational technology into the mainstream extremely fast. For a long time, this technology was available only for a few tech companies and hardcore academic researchers. But all of this has changed as cloud technology entered the mainstream. Compute power and data became more available, and quite literally, machine learning started making an impact across almost all verticals, including finance, retail, real estate, fashion, healthcare, agriculture, and so on. So it moved from being on the peripherals into a core part of almost every vertical. According to IDC, the AI and cognitive technology spend for this year will exceed $50 billion US. Gartner predicts that by 2024, 75% of companies will move from piloting to productionalizing AI. Deloitte says that more than half the companies think that AI will transform their business in the next 3 years. Now, for you to be successful with machine learning, you need to pick the right use case. And today, I'll present to you a simple framework so you can do just that. So there are a few hallmarks for putting together a good machine learning use case. So to get to this, you need to ask your team a few questions. The key is to balance speed with business value. You will want to find a use case that can be completed in 6 to 10 months. You also want to make sure that your use case is solving a real business problem. and is important enough for the business so it gets the attention and adoption. If not, it's going to sit in a fun experiment category. You also want to look for places where there's a lot of untapped data. And also, please, you need to also make sure that this problem can be solved from machine learning, and you're not solving a problem that isn't actually broken. So for you to find a good machine learning use case, I will walk you through a simple technique that has 3 dimensions against which you'll assess your use case: data readiness, business impact, and ML applicability. So a use case that is high in business impact but is low in data availability and ML applicability will leave you with an unhappy data scientist, as you can imagine. High availability of data and ML applicability, but little to no business impact, is a good prototype to experiment, but will not bring meaningful value to your organization. So you want to find a use case that is high across these 3 categories. However, 2 out of 3 is also a great place to start. So you can list your use cases on a table as shown, and a use case that is high in these 3 dimensions can get a higher priority. Now, use cases vary by business needs, but today I'll walk you through 3 use cases that are common to our customers across multiple verticals. Intelligent search, personalization, and augmenting repetitive human visual tasks. So let's talk about our first common use case, which is on finding information quickly and accurately. In today's workplace, a lot of unstructured data is generated from text documents, web pages, images, audio, and video on almost a daily basis. As a lot of enterprise data is unstructured, it's hard to search and discover data and look for insights for you to get insights, to make predictions, or to make business decisions. Employees across departments in the organization, including finance, engineering, research, sales and marketing, customer service, HR, they all need very specific information to perform in their roles. Keyword-based search engines lack context, because of which they're often inaccurate. And according to IDC, 44% of the time, employees do not find the information they need in order to perform in their job. So Amazon solves this enterprise search problem using Amazon Kendra. Kendra is a highly accurate, simple to use, intelligent search service that is powered by machine learning, and it uses natural language understanding and reading comprehension to deeply understand content and questions. So in that way, Kendra reimagines enterprise search for your applications and web pages so that your customers can find the information that they are looking for, even when it is scattered across the organization in multiple locations and content repositories. Also, it is a fully managed service, which means you don't need to provision any servers and no ML models to build, train, or deploy. Leading industry names like TC Energy, 3M, Woodside Energy, and others have implemented Kendra in their production systems today to power their enterprise search. 3M uses Kendra to connect its data scientists across years of research so they can innovate faster. Our second common use case is on personalization. In a time when organizations are depending more on digital channels more than ever, creating personalized user experiences and triggered marketing communication is essential to cut through the noise that a customer goes through on a daily basis. According to a 2019 McKinsey study, organizations that have implemented personalized recommendations and targeted communications have increased their revenue by 5 to 10% and the efficiency of their marketing spend by 10 to 30%. However, many organizations are struggling to realize and implement personalization for their users. Irrelevant communications and recommendations frustrate customers, leaving them dissatisfied and ultimately resulting in lost sales. Now, Amazon.com has pioneered personalization in 1998 when it offered an array of services for its book buyers through instant recommendations from its large catalog. Since then, Amazon has leveraged decades of research in personalization to improve customer experience across Amazon.com, Prime Video, Amazon Music, Kindle, Alexa, through recommended items and content widgets. AWS offers two approaches for organizations to implement personalized experiences for their customers. Customers that have data science teams and want deep customization, they can use Amazon SageMaker, our ML service, for building, training, and deploying any ML model quickly and also with more efficiency. Now, customers that have smaller data science teams or none at all can quickly get started with Amazon Personalize. Amazon Personalize is the fastest and easiest way for you to realize and implement personalization for your users. It enables you to quickly build applications using the same technology for personalization that is used by Amazon.com. Also, this is a service using which you can implement real-time personalized user experiences at scale. So you can engage your customers, convert them, and also improve your revenue. Industries across verticals like Subway, Lotmart, Pulse Live, Zalando are using machine learning to implement personalization for their users. The Subway restaurant chain offers guests in over 100 countries quality ingredients and flavor combinations in nearly 7 million made-to-order sandwiches created daily. They use personalization to quickly and easily implement personalized recommendations for their customers. Zalando is using machine learning to steer their campaigns better, to generate personalized outfits, and to improve their customer experience through personalized recommendations. So our third use case today is on augmenting repetitive human visual tasks. Now, extracting contextual information and metadata from your images and videos can not only help you in search and discovery, but also to automate repetitive visual tasks such as finding objects, scenes, locating individuals, their activities, identifying their faces, and so on. Now, doing this manually is not only time-consuming, but also error-prone, complex, and expensive, especially when you have to analyze millions of images and videos. AWS Amazon Rekognition makes it easy for you to add these image and video analysis to your applications. Amazon Rekognition is based on the same proven deep learning technology built by Amazon's computer vision scientists to analyze billions of images and videos daily. So this is a service that doesn't require you to have any machine learning expertise, and using it, you can quickly analyze any image or video. Amazon Rekognition Custom Labels is an extension to Amazon Rekognition if you would like to analyze an image or identify objects that are very specific to your business. For example, using custom labels, you can classify machine parts in an assembly line, find your logos in social media posts, find animated characters in videos, distinguish healthy from infected plants, even locate your products on store shelves, and also classify documents such as passports or driver's license, as well as maybe detect damage in electric poles based on their visual characteristics. Now, Amazon Rekognition comes to you through an API that you can directly call. And the extended capabilities of Rekognition Custom Labels come to you through 3 simple steps. In step 1, if you have labeled images, you can load them using the console or just by calling the API. But if you want to label your images, the console gives you a guided experience for doing that as well. Once your images are loaded in step 2, you can train a model. It requires no coding and no ML expertise is required for doing so. And once your model is trained and deployed, you can make inferences against it. It's fully managed and it offers you a scalable API. You can get good results using just tens to hundreds of images instead of tens of thousands of images. AutoNet's mission is to automate the car insurance claims process. They use Rekognition Custom Labels today to detect the extent of damage on a car and make this technology available to insurance companies so that they can in turn improve their end customer experience. Ella Credit is a young Nigerian company that is innovating in the finance and AI ML spaces. They use Rekognition and its face comparison features to verify the identity of their applicants. Last but not the least, University of Arkansas will be using Rekognition Custom Labels to detect weed in soybean crops in an automated manner, applying it on drone imagery, and Jason in the next few minutes will give you a deep dive on that use case. Now, if you would like to implement machine learning on your use cases, AWS experts will be happy to help you and your team in deriving insights and creating value out of ML. Now, all of you have come to the DC Summit today to learn, and you can continue this learning even after the summit through AWS training and certification. We offer over 65 courses at no cost, on demand, as well as virtual instructor-led training classes. When you're ready, you can also sign up for AWS machine learning certification that will validate your skills as well as it gives you an industry-validated credential. For more details, please visit aws.training/machine learning, and please look up at the AWS ramp-up guide when you're there. Thank you once again. Now I will hand this over to Jason.
Thank you, Raju. I appreciate the introduction and also your assistance throughout this project. I'm very excited to be here to be sharing a little bit about our use case at the University of Arkansas, where we used Rekognition Custom Labels to detect weeds in soybean crops. This is an interesting intersection between obviously a continuously emerging technology, machine learning across industries, with a very old problem. Weeds competing with the crops that we value and produce for consumers. And so in this, again, my name's Jason Davis. I'm really wearing 2 hats today. I'm representing both the University of Arkansas Systems Division of Agriculture as an employee, where I'm an application technologist. What this means is I actually work in the fields with producers on their application equipment, specifically their pesticide sprayers applying pesticides, and nutrient or fertilizer equipment applying fertilizers and soil nutrients. And so I try to help them, these producers, maximize the efficiency of their systems to minimize input costs and making sure that these nutrients and pesticides are applied at what would be legally labeled rates to make sure that the systems operate most efficiently, maximizing profits and minimizing these inputs. This project, in the context of that, this project had also several contributors that I want to acknowledge. Karen Watts-DeSico, Dr. Tommy Butts, Ashley McCormick, and Noah Reed has assisted either in the merging from my program's data to AWS or in the field work. Now, at an AWS conference, you probably don't often hear about field work, literal, actual working with the dirt field work, but that's the case here. In addition to that, I'm also, the second hat I'm wearing is the University of Arkansas Department of Geosciences and Center of Advanced Spatial Technology, where I'm a PhD student trying to work with merging geospatial data, satellite and drone imagery, and machine learning and AI workflows into these current workflows that we work with our producers. And so the idea is how can we continue to become more efficient with the swelling data available through these remote sensing artifacts. And so within that context, I would like to recognize my committee members and my advisor, Dr. Jason Tullis, all of which have contributed to these workflows and assisted in this project. And finally, I would like to introduce to you a couple of machine learning expert users, my kids actually, who will be demonstrating the use of an object detection algorithm and extracting a use or a purpose for that. So these are aspiring Arkansas Razorbacks, right, doing their modified hog call. But what's always intrigued me about watching my kids work with common apps that you may have on your phone is how simple the interface is and how they're extracting their entertainment and their value out of, in this particular use case, out of that app. But it's doing some very technical things behind the scenes, right? And so this is amazing technology that's becoming more and more accessible in more industries. And so this acts as kind of a loose inspiration for the project that we'll talk about today. And so you may have heard in the news in the last several years about super weeds in agricultural industry. The one we're going to talk about today is one prevalent in the Mid-South United States, is Palmer amaranth, or commonly known as pigweed. This is a fierce competitor with our crops in agricultural production and competing for soil nutrients, water, and so outcompeting will reduce our crop yields significantly and can take over fields very quickly. To put this into context, this weed in competition with our soybean crops, meaning that it's, again, not getting all of the nutrients it needs, it can produce 150 to 200,000 seeds per plant for the next generation. So multiplying 150 to 200,000 fold with each generation after you leave one plant to come to maturity. And so as an example, if you were to, if 10% of those were to emerge and the pesticide systems that we use currently in place, it has one escape, you're still the next year having to deal with 150 to 200,000 fold of the problem. And you see how these super weeds can overtake fields very, very quickly. And so timely observation of these emerging weeds is critical. And so here's an example of a soybean field it doesn't really even look like a soybean field. It's been really taken over completely by this superweed. And in addition to that, many of the tools that we've used traditionally, our pesticides, herbicides specifically, have become less useful. The weeds itself has learned to metabolize some of these chemicals. And so some of the chemistry that we have used in the past is we're losing these technologies. So how do we assess these fields currently for these needed timely observations to trigger these pesticide applications? Currently, we walk fields, either a producer or a scout that's hired by the producer. They're exclusively ground-based observations. And so these ground-based observations generally look something like this. They'll walk a transect of that field, and scanning left and right, you can see that we only assess very small parts of that field. Now, it's very difficult to cover tens of thousands of acres on a weekly basis doing it any other way. And this system works. We can generally catch those weeds early on and find a representative population enough to trigger that application. However, with current technology, with the use of UAS and drone imagery, we can actually capture most all of the field, or all of the field. And currently these drones and sensors are being used in agricultural fields today, oftentimes for plant health assessment or water management. And so, but can these be used to instead also do weed assessments on the entire field? And so if you were to do that, or if you were to ask that question, you would have to manually inspect each image or manually inspect the imagery as a whole. And so that becomes obviously very time consuming and cumbersome. When I fly, say, an 80-acre field, I come back with 10 to 20 gigabytes of imagery. And so to do that over multiple fields over multiple days, it becomes very cumbersome to do this analysis manually. And so if there was a way to automate this system and either to bring up reports or to highlight the weeds so that you can scan for location, this would be very helpful. And so that's exactly what this project attempted to do, is to scan these fields using our raw drone imagery, processed through an object detection algorithm, in this case, AWS's custom recognition custom labels, and to produce field imagery with labels on it indicating where the weeds are. And so this is kind of the context of our project. With this and your business practice or your business use case, it's important to understand what accuracy means in machine learning. And so oftentimes as you read through machine learning papers or reports, you'll see reported accuracies in precision and recall. What does that mean, and which end of the spectrum should you be on in this consideration? You really need to understand what questions these particular accuracy metrics are asking. Precision, on one hand, is asking when a prediction is made, how true is that prediction? Okay. Whereas on the other hand, slightly different question, recall is asking of the true or accurate objects in that frame, how many of those are captured by the algorithm, essentially dictating or measuring how many are missed. So some common examples for framing this appropriately is your email inbox. Generally, you have an algorithm that's filtering out your spam mail. If that algorithm were to lean very heavily on recall, you would have a report from that algorithm that says, I captured 100% of your spam email, erring on the side of accuracy, in this case, accidentally throwing away that email from your boss on that emergency meeting this afternoon, right? This would be a problem. And so generally these algorithms will lean on the side of precision and say, I captured 100%, or 100% of what I captured was a spam, erring on the side of missing a few spam in your inbox. And so you can see the need for filtering by what type of accuracy you're looking for. On the other hand, a scenario where you might lean heavily on recall would be in medical testing for diseases or sicknesses. So if you had 5 patients in this case that came to a doctor's office and that were sick, 3 of which have an actual an infection of a particular disease, if you lean heavily on precision, a model would say, or a test would say, that all of what I captured were sick patients with this particular disease or ailment, whereas I'm missing one, right? By leaning heavier on recall, you end up capturing 100% of those patients actually infected, although your accuracy may fall short and have some false positives. So understanding your question, your data, and what type of metrics you need to base your results on are important. In this use case, because of the timely observations necessary in our fields and the need to not miss weeds, we wanted to lean very heavily on recall. Mistaking a few soybean plants in the process as a weed is acceptable in this case. And we did that using three different, and I'll go a little bit deeper in that in a second, but three different tests that we used that you may find some parallels with some of your data. Just to provide some exposure to what you might see in the user interface, the training data that you're going to use or the imagery that you're going to use is going to be broken into training and testing data. In this case, we used high-resolution RGB imagery acquired by low-altitude unmanned aircraft systems, UAS flights, 60 and 90 feet in this case. We, again, broke the data into 80% training data and 20% testing data. And so the model actually never was able to see the testing data until it was testing basically the parameters that it produced. Here's an example outputs in our use case of some of the field imagery. So again, this is an overhead perspective from the drone. And you see three images here that's been labeled by Rekognition custom labels. The green bounding boxes are actual weeds that have been identified. The red on the far right image is actually a weed that was missed, a false negative in this case. And so you can see that it did a pretty good job. This was an initial test we did, just kind of a proof of concept. We only used 500 images in this initial test. Now this is really amazing in my opinion. The technology 5 or 10 years ago would have required hundreds of thousands, if not millions of images to produce these types of results. But through transfer learning, there's much of that image structure and the understanding of what to look for is already built into the system. And so minor tweaks on the tail end of these parameters is all that's being adjusted with these very small image sets. And so in this case, 500 images produce a precision of 0.97 or 97% accurate essentially, and nearly obtained 80% or 90% recall. So we captured 80 or 90% of the field's image or the weeds in this particular field. So this was, in my opinion, very, very impressive. And so from that, we said, how can we increase recall? And we did 3 quick tests. The first hypothesis, we theorized that the model recall would increase with an increase in training samples. Now this makes sense. If you're going to feed the model more and more images, then we would expect the recall to increase. And so the imagery again was taken at 60 feet. We used 250, 500, 1,000, and 1,500 images. Now, if you're manually labeling these images, which I did, you're looking for that top threshold, right? You're ready for this process to stop because this can be painful if you're not careful, especially if you're looking at hundreds of thousands of images. And so this was important to find that top threshold. And so these are the results from that particular data set. And so you can see the blue bar, 250 images, up to a maximum of 1,500 images, and you see our precision held and did increase as well as our recall increased. But we seem to have a plateau between that 1,000 and 1,500 images, meaning that in our particular use case with this specific example, that we ended up, that was where I could stop labeling essentially, right? And so 1,000 images seemed to work. And so some of the results we built upon after this was based on 1,000 image sets. The second thing we did to try to increase our recall was that, or to test, is that we theorized that as we increase the altitude of the drone, the imagery, that would coarsen the resolution of the image, right? So if you've got a camera that's framing an image on the ground here, the further you move away from it, the coarser the resolution your image would be. And so if you were able to capture, let's say you've got an 80-acre field that takes you 20 minutes to fly, if you could fly at a higher altitude, you could capture the same acreage at a much shorter time with much smaller amounts of data. And so we expected that to decrease our recall because the model was fed coarser resolution imagery. And so as an example, we used 60, 90, 120, and 180 feet. In this case, the last 2 data sets, 120 and 180 data feet, were generated using a GIS system to basically coarsen those pixels and represent what that flight would look like because we actually only had the 60 and the 90 data sets. And so with that, to my surprise, well, first off, model recall and precision did drop slightly, But we were able to expedite the data collection and the processing by fourfold by running these higher altitude flights with only a 2% reduction in model recall, which was, in my opinion, that's large steps forward in system efficiency with minimal losses in accuracy. And so this was an important threshold to recognize for us. And finally, we suspected that if we were to break the sizes of weeds into different categories, that we might increase model recall. Now, this would make some sense. From your perspective here, you can see the two weeds that are labeled. Those could be, from a computer standpoint, labeled as different objects. And so it could, in theory, confuse a system by lumping them into the same category. So we separated them out and tested it to see if we could increase our recall. So we trained and tested a model with exclusively weeds, and then trained and tested a model with different weed classes based on their sizes. And so here are the results of that. The blue bar, again, is a single class, and the second pair of bars there are a single model and then representing this classes, the accuracy of each class. In this case, surprisingly enough, the model actually did as good or better with a one class, looking for one class of weeds. And so that was nice. That means in our case, we're only interested in knowing whether the weed's there or not, or in our next use case I'll share in a second, how to attack or spray those weeds. We don't care really if they're in separate classes, and it didn't help the model any. And so that was good news. So in summary, Amazon's Rekognition custom labels, as a scouting aid in this case, 1,000 images seem to show the model enough information to produce accurate and somewhat reliable results. Imagery collected from higher altitudes produced up to 3 times coarser resolution, increased system efficiency, but only minimally reduced our recall or overall accuracy. And then separating the weeds into separate classes, it really had no impact or provided no advantage at all. And so this system, this workflow shows promise as a scouting aid at detecting these weeds in our systems. There is more work to be done. Agricultural systems are incredibly variable between crops, weeds, soil types, and so there's more work to be done to incorporating more and more training samples to make these more robust systems. But the initial tests, again, show to be very promising. What if we could take this one step further, outside of just a scouting aid to trigger a pesticide application? Precision agriculture is a term that's used to try to better place inputs where they're needed most. It has been limited in the past by both the acquisition of whole field imagery, or whole field data rather, and the ability to analyze it in an efficient way. This has been cited as requiring these workflows requiring 3 different components, and these make a lot of sense. You've got to be able to collect the whole field variability through a sensor system that's usable. You've got to be able to have an information system that can take that information, that data, and extract the value out of it that you're looking for. And then finally, if you're going to actually place those inputs, whatever those inputs are, in this case we're going to talk pesticides, if you're going to place those pesticides only where they need to be, you've got to have equipment that can leverage that data in the field. And so I'm here to suggest that we can do that. First off, I've already mentioned the UAS system, so the drone imagery, machine learning through Rekognition custom labels, and then we'll leverage a few other software packages here that categorized as geographic information systems. And then from my background in the field with technology in pesticide application equipment, I'm here to suggest that modern sprayers can also be an integral part of this workflow. So currently, it's important to note that all pesticides, or the vast majority of pesticides, are what's known as broadcast, or applied over the entirety of the field. This generally makes a lot of sense. What you're seeing here are 4 different plots that have been treated with or not treated with, depending on the plot you're looking at, what's known as a pre-emergent. Pre-emergent pesticides are those that are preventative. So you want to treat the entire field to prevent the emergence of weeds, right? That makes sense. And you can see the contrast between the first plot and the third versus the second and the fourth. And so that's where a pre-emergent was applied. This acts essentially as a chemical net. It's like a vaccine for the soil, essentially, to stop the growth of these weeds. This makes complete sense, broadcasting this. And there are other pesticides that's the same case. However, there's a second group of pesticides that are known as post-emergent, only targeting the weeds in the system. We still broadcast these pesticides because there's really, at this point, very little other ways of doing that. And so we broadcast, and we actually, even in post-emergence, we will apply the same amount of pesticides to the first, second, third, and fourth plot, even though the only target organism is the weed in this case. So you can see the excessive amount of pesticide that, again, is legally labeled and has been thoroughly tested and is appropriate, but you can see the potential for savings and reduction in environmental impacts here. So in our production systems in Arkansas, particularly in soybeans, herbicides account for nearly 20% of the operating costs in these systems. And so there's a lot of money that's gone into these to protect and preserve these actual, the crops that we're trying to grow. And so there's opportunity here. Opportunity for both reduction costs for the producer and reduction in environmental impact. The challenge here, though, is to be able to site-specifically apply, meaning apply only where needed. You've got to be able to locate those weeds, and this is a manually labeled image set in this case, but you can see the contrast between those fields represented by plots. So the information system, again, we've got the UAS part we've already mentioned, but the information system, in addition to a machine learning algorithm, is, in this case, we're going to need a GIS system. Geographic information systems combine data with location information. You probably used at some point in the last couple of days to get here your cell phone with a mapping app that walking down the street or driving a vehicle. And we generally refer to those as GPS apps. Let me pull up my GPS. It's more accurately described as a GIS system, which leverages the data in the background, where the restaurant is, where your location is, what services are around you, with GPS information or your location. In agriculture, these types of GIS systems has allowed us to organize these swells of data that's in the field, whether it's the soil tests that we pull in, the weed maps that we're fixing to look at, aerial imagery of plant health. And so we can organize and visualize these to help better make decisions. And in this particular workflow, we're going to look at how you can not only identify the weeds, but find their location in that field and act upon that using 3 different software packages or software options here. The first one we're going to look at is Pix4D Mapper. In this case, we take raw drone imagery, and this particular software actually pieces together those raw drone images like a puzzle. And so each of these green dots represents a single image from the drone. This particular package will analyze do a key point analysis and actually look at where those images overlap and produces a 3D structure of that crop canopy using these key points. And so now we've taken what was a single image or a group of single images, and now we can have a single layer across a whole field, a 3D representation of that field. From there, this produces what's known as an orthomosaic. An orthomosaic is a perspective adjusted or is a image that is free of perspective distortion. Meaning that no matter where you zoom to in this field, it looks like you're immediately overhead. That way you don't have any crops that are occluding the soil conditions based on your perspective that's off of the center of the image. So in this case, you see the soybean crop with a single pigweed in the field. From here, we can pull this data into, or this orthomosaic into ArcGIS Pro, which is a geographic information system that helps us analyze. We can remove background effects, extracting just from the field. We can reorient the images. In this case, we're going to take and lay over what's known as a fishnet, a grid, that is correlates to the size of the frame of the original drone image, so that recognition custom labels, or the algorithm that we're going to use, can actually look only within that frame and then analyze it for weed presence. And so that's what we do. We can ship those individual frames to Recognition Custom Labels. The weeds can be labeled in this case, and then we can pull that puzzle piece, since we know where it's at and where the weed is contained, back into our workflow in ArcGIS and reassemble the puzzle. And if you look carefully here, you can see all of the green bounding boxes across that field. Whoops. From there, we can remove the fishnet that correlates to the images, or the drone imagery, and overlay a new fishnet, a new grid. This represents the resolution that we can treat with our machine or our sprayer at the end of the workflow. And so again, they're operating at different resolutions, and this would be variable depending on from one machine to the other. In this case, it's 1 meter square grid. So this is saying that each square meter, instead of the entire field, will be analyzed for the presence of a weed. We can once we overlay this, we can highlight or select those square meters that contain a weed that was identified by the algorithm and extract that as a separate layer. So there's our separate layer. And we can actually remove the background imagery. So now what we have is georeferenced or localized polygons that are areas to be acted upon. In this case, it basically is a layer of zeros and ones. The equipment should be off or the equipment should be on as it traverses this particular area. So how about that equipment I mentioned earlier? Today's sprayers actually operate using highly responsive solenoids on each nozzle. And these nozzles are spaced between 20 inches, or between 10 and 20 inches generally. In this case, we're going to be operating on a 1 meter grid. And so that would translate basically to 50 centimeter nozzle spacing, and each grid would be occupied by 2 nozzles essentially. And so each of these nozzles have a solenoid that kicks the nozzle on and off. Now this is currently only used for, we also have field computers that can read maps, such as what we've produced here, but generally this is only used for turning off the sprayer as it exits the field. So as you approach a field boundary, those nozzles will kick off, but again, the rest of the field is broadcast. And these on-off solenoids also allow us to adjust rate. So as you increase the speed that you're traveling through the field, the flow rate through those nozzles needs to be increased to hold rate steady throughout the field. And so these systems are very finely tuned to hold very specific rates, again, that are legally labeled, but they're only used for blanket or broadcast applications and to turn nozzles off in the fields. But this technology with high precision GPS can be used, in this case, to selectively spot treat that 1 meter grid that I mentioned earlier. And so the very high level look at our workflow here is to collect raw drone imagery, process it through this machine learning GIS workflow, and then produce site-specific maps that can be treated grid by grid, 1 square meter by 1 square meter across the field. So here's the research we've got ongoing. This is a research sprayer that I've modified with a boom that represents it's very similar to what we see in production systems. This particular system leverages Capstan Ag Systems Pinpoint 2. Thank you to Capstan Ag for their assistance in tweaking these workflows to fit their structure and assistance in the field. This system has a field computer that can import the outputs from our machine learning AI workflow, GIS workflow, from that field map created from drone imagery. And so it can read it in the field and turn nozzles on and off. So here's a drone videoing the sprayer as it traverses the field. What I want you to watch carefully is on the front of that system, there's about 7 spray nozzles. And if you look carefully, they will come on and off. Now, you're not going to be able to see the weeds here because they're, again, embedded between the rows. They're small. We're trying to catch them very early and very young. But what you're seeing is completely automated. again, from drone imagery through the algorithm, and the output would be the weed map, and then the machine can read it on the go. There we go. So the system's kicking on and off based on each square meter grid as it traverses the field. And again, it's fully automated. How about results? So this is from a different set of plots. The weeds are a little bit larger here. And so current field test, you'll see some red lines in the imagery here that represent different plots. These are the results from an algorithm output in this case. And so you can see the purple bounding boxes around each image or each weed. In this case, we've broken the plots into separate treatments. So on the far left, you see a broadcast treatment, again, what the current field work would generally represent. The third plot there, you see there's no spray at all, and that's going to be what's known as an untreated check, or an area that's left untreated for comparison's sake. And then you can see two strips, strip number 2 and 4 here, in this case, that will be spot treated only. Okay? So this is the results 1 week after treatment, and you can see the reduction of weeds in each of the 3 plots by comparison, the untreated check. And so early data suggests, apologize, my clicker doesn't seem to be liking this very much. So as you can look, current system, the way we currently do things, 100% sprayed. We had 94% control through visual observations. By comparison, you see 0 sprayed, 0 control. And then our machine learning workflow here used 35% and 15% in different plots, achieving nearly as good control as that from the broadcast treatment. So you can see the potential reduction of pesticides introduced into these systems. You see the potential for both cost savings for our producers as well as reduction in environmental impact. Now, I do want to take note, these ratings were taken visually at 7 days, essentially asking the question, were the weeds hit by the sprayer? Was the pesticide deposited? And then you saw the results a second ago that the weeds were dying. As you look further and further out, the question becomes, did the weeds stay dead? And I know that sounds like a silly question, but some of our resistant weeds will actually die and then they'll come back. And so they appear to be dead, but they're not fully. And so there's still more work to be done. And these were actually relatively large weeds, but so some of them did come back. But early indications, meaning that the sprayer was able to read and spray. Again, the video you saw earlier was of smaller weeds. Those died. Okay. So here's a scaled up version of our plot. So you can see the spot treatments and the untreated checks scattered throughout there. And so we moved from small plots to strip trials to hopefully looking at full field trials next season is the idea. So conclusions. The intersection of agriculture, remote sensing capabilities like drone imagery and satellite imagery, and machine learning technologies have the potential to revolutionize our current agricultural production systems. Automated and semi-automated workflows have great potential to both reduce the input burdens and for cost savings for our producers, while also reducing environmental impacts. And in this case, that's a win-win. And so by reducing the inputs, cost savings, and then we have reduction in environmental impacts. So it's a very exciting time to be working in the space, the machine learning, AI space. It's also a very exciting time to be working, in my opinion, in agriculture. Now, with all that said, there's a lot of excitement, and I get very excited about this kind of work. I think this is very promising and exciting moving forward, but there's still a lot of work to be done. There's still a lot of how well does this generalize across other production systems or even within the fields that are similar. And so while I get excited, I oftentimes have to step back and say there's a lot of more work to be done, which is good. That's job security for me, right? Okay. With that, I appreciate your time and thank you. And I think Raju and I will open for questions if there are any.
Thank you. So if you have any questions, we'll be happy to take those.
Yes, sir. Yes, sir. Thank you, Mr. Davis. That was a very interesting presentation. I wish you good success in that program.
Thank you.
I have to say that I'm not from Arkansas, but if I were a pigweed, I'd be a little disconcerting. Think you've got the lasers about to take me out, you know. Nonetheless, my business is not pigweed, unfortunately. I'm in the contracting data, legal data type of a business. So to you, Mr. Pinchak, I ask, is there efforts being made using AI or ML for interpretive type of thing, trying to use machine learning for intent, trying to read data and interpret what is meant by the data that you're reading, not just merely using algorithms to identify tags, but to also to understand what is the purpose and the intent of the data that is being translated. Thank you.
Yeah, well, I'll take that question. So, yeah, so the question was, like in legal field, how to understand the intent or the purpose of a question and how to use machine learning for those reasons. So the thing that comes to my mind is natural language processing and text analytics have advanced quite a bit in the last few years. And AWS has implemented services to take that advancement or even push it further. And Kendra is what comes to my mind. And because Kendra uses very advanced NLP techniques to understand the intent, and it can also, by understanding the intent, it can answer questions. So let's say you have captured the data and then, in text format, you can ask some very specific questions. And unlike keyword-based search engines, which will many times miss the intent, Kendra is built for that purpose. So it will try to find the intent and then show you answers based on your question by understanding the purpose behind it. So maybe we can talk further in the corridor, but that's what comes to my mind.
Hello, my name is Tim Tang with Hughes. That was a brilliant case study. I have a question for each of you. Jason, it seems like when it comes to AI models, the weakest link is the training of the model, like looking through 1,500 images and the like. I was wondering, as you did your case study, did you consider any other algorithms or any other approaches that would require, or are you aware of any other research that requires less training of the models or a less onerous kind of activity? I mean, you're dealing with things that are growing. Was there any kind of thing of looking at the imagery over time, for example, or something like that?
We look at the imagery over time to automate that step. That is a challenge because a lot of our fields we fly on a weekly basis to capture that temporal effect, because you're right, it's an evolving system. You're looking at one point in time and you may be just making that decision at that point this year, but next year it may be a week later or a week later. And so we capture that data and we try to incorporate that into the training process. As far as, was your question, are there systems to automate that?
Yeah, other ways of reducing the onerous process of training the models.
I oftentimes will leverage in some of our GIS packages that I mentioned. There are some embedded algorithms that assist with training data development. So I'll label a subset of images, allow the process to essentially guess with certain confidence levels at finding other artifacts in that imagery, and then I will truth it, essentially, verifying that before it goes into any kind of next process. And so there are some that I have leveraged within the GIS systems. I don't know if that answers your question.
Could I also just add one quick thing? What we have noticed, like one of the experiments that Jason has presented was if you divide that into two classes, one with small weeds, one with large weeds, if you have noticed that it didn't make much of a difference. The reason is these computer vision algorithms, they look for various things like the structure of the leaves compared to its surroundings. In this case, the structure of weed leaf compared to the soybean. That's why having like a large weed image versus smaller image didn't make that much of a difference. So I think, at least in my opinion, that the idea here is to train the model only once in an ideal case, right? And hopefully apply it across various growth stages of the weed, and also hopefully across various geographical locations. Jason, you were experimenting with various light conditions and various environments, right?
We were looking at time of day when the drone imagery was taken. If you think about, where the sun is in the sky, it's going to it'll light the plants differently. And actually, some of the imagery that we used here were plot work for training data, and they were staged by growth stage of the weeds. So what I captured on one day was 3 weeks of different growth stages. And then the next week was similar, but 3 different weeks, 3 examples of 3 different weeks of growth stages. And so we try to simplify some of that in data collection.
But that's the ideal thing.
Right,
That's the ideal scenario. However, reality is a little more complex than that. But that's where we need to iterate a little.
Excellent. Well, thank you. Roger, my question for you was, there are a lot of retailers who would want to use and take advantage of these capabilities, but they compete with Amazon. How can they use a managed analytics service and then be assured of protection of their data?
Oh, great question. So the question was how data of the user or the user organization in this case is protected. So all the data that's on AWS belongs to you, right? And there is also you can sign up that sometimes our ML or AI services, if they use your data for improving the training of these algorithms, there is a provision for you to sign off saying you don't want that. But at the same time, your data is securely in your account and nobody else can access it. And the models that you build, any custom models and so on, like custom labels models, for example, in this case, Jason's model, are purely your models. No one else can have access to.
I can vouch for some of that because we had trouble communicating between my data sets and his, because he didn't have access to a lot of that. So if I had a question, we had to find ways around that I approved,
So I actually have 2 questions. First question, why not just put the camera on the sprayer? And the second question, if you're using these machine learning algorithms to look at the leaf structure, wouldn't the weeds just evolve different weed structures over time? And therefore, wouldn't you be constantly having to retrain these programs to identify the weeds?
2 excellent points. One, there are other companies and other very, very smart, very talented companies and people that are working on this problem. And some of the workflows they use actually do mount the cameras on the booms. The trouble that some of them, from my understanding, what they run into is that first off, they end up running into some lighting issues related to capturing that imagery. They run into different problems than I run into because of the remote sensing, the way I'm collecting the data. They also run into the processing loop between detection, the decision made, and then actually taking action on that weed in the moment. Much of our equipment currently operates at about 16 to 20 miles per hour. And so to traverse that field and detect and spray in that instant becomes a challenge in processing speed to make that happen. Obviously, that technology will evolve, and that may not be a bottleneck or limitation in the future. But right now, that's been a challenge, and they've had to limit their speed to somewhere between 2 and 5 miles an hour. Advances have been made. I'm not real sure where that particular company is right now on how fast they can operate. So the advantage to this particular workflow is we can, in this scouting step we're already doing, collect imagery ideally at an ideal time of day, and then that imagery can be used in the workflow, and then you can look as a producer at the map and almost provide some reference to, yes, this looks accurate, or we need to adjust some of the parameters in this. Whereas if you're limiting that exclusively to be automated in the field, there's a potential for that for more mistakes to be made that you can't foresee. And so there's a second part to that.
My second question was the evolving of the weeds. Wouldn't they just evolve different weed structures, and you'd have to constantly be retraining?
Mother Nature is incredible at this, right? And so essentially you're suggesting, which you're right, if we're imaging what we see as a weed, then we're going to filter by weeds that look more like our crops.
And so eventually the weeds that are left are going to look exactly
Are
like
going to
the
look
crop.
like our crops. And that's basically what's happened with the chemicals currently. They've developed resistance. We have filtered by weeds that have a better metabolism for these chemicals. And so what's left in the field generation after generation are weeds that can metabolize our crops. So you're right. You would have to essentially update your training data set for each. And I'm a proponent of that these models are not going to be, in general, one size fits all for all production systems. I think we're going to have to train and retrain over time and update these to provide libraries of comparable training data for our producers because there's such variability in our production systems.
Can I ask a quick follow-up question? How much of cost on training with this in Perpetua? You know, how much time and energy and cost would it be to keep having to train and increase these libraries to make them effective?
Training, I would say training is relatively inexpensive because you're doing it one time and you'll stop the instance, like the compute instance, once you're done.
Okay.
And just to add to one more thing, I mean, these deep learning models, they are very good but also complex when it comes to explainability. In addition to the structure of the leaf, there could be other things that it's looking at, like, for example, the soil around it, the color of what is immediately next to it, right? So I feel at least that weeds that are in between lanes are probably easily distinguishable than those that are in the crop just because of the brown mud and sand that's around them. And these deep learning models do take, in addition to the leaf structure, all those things into account.
Then
Right.
couldn't you use the weeds between the lanes to help train the weeds in the lanes?
Sorry.
Couldn't you use the weeds in between the lanes that you know are more probably not part of the crop to help train to look for the weeds that are in the lanes?
Yeah, so we would have to still experiment with how they will work if they are in the lane itself, because again the surroundings are different. So we'd have to see how the model will work in such a way.
Right. So you could look at see a leaf that's outside of the lane, and then say, okay, that must be a weed, and so you look for one that's in the lane. See what I'm saying?
You're assuming that the genetics would be the same between the two. So by isolating the one that's in the lane, that you could therefore find the one that's in the lane.
Correct.
Right. Yeah, that's a fair assumption.
Yeah, but we would have to again run experiments to see if that makes any difference. So, but at the same time, the point that I'm trying to make is that it does take other things into account in addition to the structure of the leaf.
Okay, thank you very much.
Thank you. By the way, we try to improve our sessions through your feedback. Please give us feedback by just scanning that QR code, or it will also be on your app.
And I am loving this discussion, but because of the keynote that is starting in Hall B very soon, we do need to wrap up. Please, if you have additional questions, connect with Raju and Jason after, but please complete the session survey, and if we can all make it to Hall B for the keynote, that would be wonderful. But please give them another warm round of applause.
Thank you, Stuart.
Thank you.